Section 7.4, adding, subtracting, and multiplying radical expressions. So we're going to start off adding and subtracting. How you do this. You want to do like radicals. So radicals with radicals, they have to have the same index and the same radicand. So unless the radical looks identical, you cannot add it together. It's just like x and y. Like radicals can also be combined with addition or subtraction by using the distributive property. So example 1, our first one, what we're looking for is for the radicand to be the same. The radical needs to be the same. And remember, there's always an imaginary 1 in front of everything. So we have 1 radical 3 plus 7 radical 3's. That means we actually have 8 radical 3's. Okay, we're going to do the same thing here. We're good to go because the radicand is the same. So if the radicand is the same, we have 10 radical 2's minus 4 radical 2's. That's just the same as 10x minus 4x. So we're left with 6 radical 2. Now, next, we cannot add those because 5 and 3 are not the same on the inside. So the 5 is just like x, the 3 is just like y. They're not the same, so it's already simplified. And the same thing for D. A big thing that we need to keep a lookout for is this index. The indexes need to be the same because this is saying I want the cube root of 2 and that's the square root of 2. If the indexes and the inside, the radicand, aren't the same, you cannot add them. So D is already simplified as well. Alright, example 2. It doesn't seem like we can add these, but try to simplify and then add. Always simplify, then add. So for 27, we can break that down into 3 and 9. And for 75, we can break that down into 25 and 3. So we take the perfect squares out where we can. So we have 3 square root of 3 plus 5 square root of 3. Now, they have the same inside, so we can add them to get 8 square root of 3. Example 3. Simplify, then try to add. So we can break down 20 into 4 times 5. And we can break down 45 down into 5 and 9. So we're going to take the perfect squares where we can. So we have 3 times the square root of 4 is 2 times the square root of 5 minus 7 times the square root of 3 times the square root of 5. The outside, you multiply because all of this is multiplication. So we have 6 square root of 5 minus 21 square root of 5. Now we can go ahead and subtract them because the radicand is the same. So we have 6 minus 21. So we have negative 15 square root of 5. Alright, example 4. Simplify, then try to add. So we have 3 times the square root of 5 times the square root of 9, and take the variables out. Make it its own thing. And then we're going to add that to x 5x. We can't do anything with 5x. There's nothing to simplify there, so we leave it. We take the perfect square out of the 9, so we have 3 times the square root of 5 times, and then how many times does 2 go into 3? It goes in 1 time, and we're still left with 1 over. And we're just going to bring down the rest, so plus x times the square root of 5x. So we're going to combine like terms on the left side. So we have 3 times 3 is 9, and then we also have this x, so 9x. And then we have radical 5 times radical x is square root of 5x plus x square root of 5x. Now we can add them because they're the same. So we have 10x times the square root of 5x. Alright, objective 2, multiplying radical expressions. So here, example 5, we're going to have multiple versions of expressions. Here, we distribute as the distributive property. When you multiply, it doesn't matter what's on the inside, doesn't matter what's on the outside, you just multiply away. Just the same as x and y, because you can multiply x and y, it becomes xy. So we have the square root of 3 times the square root of 3, that's 9. And then the square root of 3 times the square root of 2 is the square root of 6. We can simplify the square root of 9 to 3 minus the square root of 6. Did you notice that when multiplied the same together, it simplifies down to whatever it originally was? Pay attention to that, because that's going to come up a lot later on in this chapter. Alright, next, we have to FOIL, because we have binomial times binomial. Now, what do you notice about these? Take a look. They kind of look identical, don't they? Except the sign. That's called the conjugate. We'll get more to that later on, and you're going to see something when everything's the same, but the sign in the middle, something's going to happen. So we have the square root of 3 times the square root of 3 is the square root of 9. You can go ahead and simplify that to 3. You don't have to put it as 9. We have the square root of 3 times 8. Well, that's 8 times the square root of 3. And then we have negative 8 times the square root of 3 is negative 8 times the square root of 3. And then negative 8 times positive 8 is negative 64. We're going to simplify. The square root of 3's cancel out because one's a positive 8, one's a negative 8. The square root of 9 is 3 minus 64, so we get negative 61. You notice the square roots, the radicals, cancel out. That comes in handy when we rationalize denominators, so you'll see that again. Alright, example 6. We're squaring these, so what that means is we have x plus 1 plus 2, x plus 1 plus 2. So again, we're going to FOIL, our favorite four-letter F word. So we have x plus 1 times the square root of x plus 1. Just like when we were doing the square root of 3 times the square root of 3, we got the square root of 9, which is 3. So here, we don't have to square them. We can just simplify it to x plus 1. That always happens, and you'll see later on the semester why that is able to happen. And then we have x plus 1 times, so the square root of x plus 1 times 2 is plus 2 times the square root of x plus 1. And then we have 2 times the square root of x plus 1, so that's another 2 times the square root of x plus 1. And then 2 times 2 is 4. Now we're going to simplify. We have x, 1 plus 4 is 5. And then we have 2 square root of x plus 1 plus 2 square root of x plus 1, so that's 4 square root of x plus 1.